This line is making predictions for 36 examples, and it is visibly wrong. You can see the gap between where it says each point should be and where that point actually sits. To you, that is obvious in a single glance. Now here is the problem a computer has. It cannot act on the word wrong. It cannot look at a picture and feel that the line is off, and it has no sense at all of what the right answer would look like. It needs a single number that says how wrong the whole batch is right now, because a number is the only thing it can push in a direction. That number is called the loss, and for this starting line, it is 3.8705. On its own, that value means nothing. It is not a percentage and not a grade. It only becomes useful when it changes. So here is the question. What is loss, and how does one number teach a model to improve? This is worth caring about beyond a toy line on a graph, because that single choice of number is what decides what a model ends up doing. It sets what a recommendation feed pushes at you and what a medical triage model treats as an acceptable mistake. Before anything moves, make a prediction of your own. If that score falls, does the line have to get closer to every single point, or can some individual errors get worse along the way? Watch each vertical segment appear. Every one connects a prediction to the target it was supposed to hit. The loss takes each of those gaps, squares it, and averages the result across all 36 examples. Squaring does two jobs at once. It removes the sign, so an error above a point cannot quietly cancel an error below one, which would otherwise let a badly wrong line score suspiciously well. And it punishes a large miss far more than a small one, so the score cares disproportionately about the worst mistakes. That second property is a choice, not a law. It means this particular loss will happily accept several small errors in order to eliminate one big one. This is important, so it is worth stating plainly. The loss is not a judgment about the model, and it is not a measure of intelligence. It is a deliberately chosen objective, picked by a person, and choosing a different one would make the model learn something different from exactly the same data. A different loss would refuse that trade, tolerating one large error rather than several small ones. Neither is more correct. They encode different priorities about which mistakes hurt. Now watch the score itself over time. Every training step produces a new loss, and plotting them in order gives you the training curve. This is the number the model is trying to drive down, step after step, and it is the plot people actually stare at while a model trains. Notice the shape. It falls steeply at first and then flattens out, and that shape is almost universal. Most of the improvement arrives in the earliest steps, and the long tail of training buys progressively less. That is why training for longer eventually stops being worth the electricity, and why this curve is what people watch to decide when to stop. But be careful about what this picture does and does not tell you. It says the score is falling. It does not say the model is getting better at anything you actually care about. Those are different claims, and we will come back to the difference, because it is where most real machine learning goes wrong. Now change the axis, and the whole picture changes meaning. Instead of time along the bottom, put the one setting the model is allowed to adjust, and use the loss as height. Now you are looking at the landscape the model is actually walking down. It starts high on the left, where the setting is badly wrong, and falls away towards the bottom right. Here is the crucial part: the model cannot see this landscape. We can because we drew it. The model has no view of the whole thing at all. All it can do at any point is measure the slope directly beneath itself and take a step downhill. That is the entire method. The size of that step is the learning rate, and here it is 0.12. Too small and it crawls. Too large and it can leap straight past the bottom and land somewhere worse than it started. Watch 60 steps happen. Early on the slope is steep, so the steps are large and the line swings visibly. As it nears the bottom, the slope flattens and the steps shrink on their own, which is why the dots bunch together on the right. Nobody programmed that slowdown. It falls out of the step being proportional to the slope. The score falls from 3.8705 to 0.0093, a reduction of 99.8%. And look at what it found. Its setting ended at 1.725, while the value that generated this data was 1.742. It never was going to land exactly, because the data carries noise, and chasing that last difference would mean fitting the noise instead of the pattern. Before and after, side by side. Now answer the question directly. What does a loss function actually give a model that the word wrong does not? Take a moment before the answer appears. Here it is. It gives a direction to move in, not just a verdict. That is the whole contribution, and it is easy to skip past. A verdict tells you the state you are in. A number with a slope tells you which way to go next, and that is the only thing a model can act on. Everything else in training is machinery built around that one idea. Now the honest limits. A falling loss is not the same thing as a better model. This one fell by 99.8% on the data it was trained on, and that is the only data it has ever been measured against. A model can drive training loss almost to nothing by memorizing its examples, reproducing them perfectly, and failing completely on anything it has not seen. From the inside, those two situations look identical. The curve goes down in both. That gap between the score you optimize and the behavior you actually want is the single biggest source of trouble in practical machine learning, and no amount of staring at the training curve will reveal it. The only way to see it is to test on data the model was never allowed to learn from, which is why held-out data exists, and why anyone reporting only training loss should be asked why. So the takeaway is small and sharp. Loss turns being wrong into a direction. That is why models need one, and why the choice of loss quietly decides what a model becomes. Change the objective and you change the behavior, even with identical data and identical architecture. Now take it somewhere new. Where else does choosing what to measure end up deciding what actually gets optimized? Think about a company tracking a single metric and watching every team quietly reorganize around it. A school scored on one exam, or a road network judged only on average speed while journeys get longer. Same shape, same trap. The measure stops being a description and starts being the target. The next episode stays inside the same machine and asks how a model decides which parts of its input matter to each other, which is the operation sitting at the heart of every large language model you have used.